All right, so last time we first introduced the idea of kinetics and the rate of a reaction. So we're currently in chapter 14, right at the very beginning of section 1 here. So we are currently on page 610. So first we're going to talk about the average rate of reaction, which an average is an average over specific time. As we saw last time, as time goes on for most reactions, the reaction rate will slow down because your concentration of reactants is going down. So there's less reactants colliding with each other and your reaction rate will slow down. So when we talk about the average rate, it's usually over a specific time period. So if, example, in the last data we were looking at here, we looked at the first 50 seconds to find our average. We would look at how much our concentration changed over that first 50 seconds. Or we could look at the first 100 seconds by looking at how the concentration changes over 100 seconds, and we would end up getting two different rates in this case, 3.80 versus 3.54. So it's slowing down a little bit. The rate, therefore, is going to be that change in concentration, which in algebra, the change in a curve is going to be its slope. So from that, if we can get the region, or that average, that denominator smaller and smaller and smaller and smaller, what we can get is something called the instantaneous rate, which is the rate exactly at one point. So for a curve, to find the rate at one point, or the slope at one point, that's called the slope of the tangent line. So looking at that curve right here, the slope of a tangent line. So if I want to know just for right here at this point here, what is the rate right there, I would draw a tangent line and find the slope of that line right there. Versus here should be a smaller slope because I'm further along in the reaction. It has slowed down. So my tangent line should have a smaller slope here. So now this is going a little bit more into the realm of pre-calculus and calculus, finding the slope of a tangent line. You are not going to have to do the calculus. It will already be done for you. This is just where these equations are coming from. So later on we'll have rate laws versus integrated rate laws. Again, you do not have to do integrals, but you do just have to be able to tell the difference about when you use a rate law versus when you use the integrated rate law. So as you can see, as the reaction goes down, our rates are slowing down, 2.96, 2.09, 1.48, so it slows down as the reaction goes on. So we can have a rate law written as being directly proportional to the concentration of the reactant. So if our rate is proportional to the reactant, to make this equal, we just need some sort of constant. So that little k is going to be our rate constant. So our rate is equal to that rate constant times the concentration of a reactant. Now rate laws cannot be written in the concentration of a product because at time 0, right off the gun, where we're going as fast as possible, we have 0 concentration of product. So it is the concentration of the reactant that determines the rate. Now in this case, I'm looking at a simple equation that just has one reactant. Later we'll see what happens if you have more than one reactant. But in this case, we have just one reactant, looking at its effect on the concentration. So this is a simple rate law. Rate is equal to K, the rate constant, times BR2. By the way, in your notes, make sure that when you are writing K, you write this as a lowercase k. I say that because next chapter, in chapter 15, we do equilibrium. We will have an equilibrium constant, which is also K, but it's an uppercase K. And guess what? We get to have some equations that have both of them in it. So it's important that you keep track of what is the rate constant versus the equilibrium constant. So rate constant is a lowercase k. Next chapter we'll have an uppercase K.
The BR2, that is the concentration of the reactant, right?
Yes, BR2 in this case was our reactant for this equation. Where is our original? Here we go. BR2 plus HSCO3H. In this case, BR2, I guess, is the only one that's affecting the concentration, at least the only one that we are looking at as affecting the concentration, or affecting the rate. All right. So if we want to find the rate constant here, we can measure that instantaneous rate, again, using the tangent line, and then set it equal to whatever our concentration of bromine is at that point, and then solve for what that rate constant is. And what we find is we get pretty close to the same rate constant regardless of where our concentration is, where we are on the reaction. So here we have it for at 0.0101 molar Br2 versus 0.0042, and we got pretty close to the same K. Overall, K is about 3.5 times 10 to the negative 3 per second, or seconds to the negative 1. So it doesn't matter so much where you are in the reaction. The rate constant should be constant throughout the entire reaction. Now, it's also does not, although the rate constant is not affected by the concentration of bromine, it is affected by temperature. And we'll have equations later for what happens to that rate constant as you change the temperature. Because many reactions are dependent on temperature. As you increase the temperature, that affects how fast the reaction goes. So later we'll have an equation that will change that rate constant if you change the temperature. All right, so looking at this reaction here, now I'm looking at a product that is a gas. So although we started with, in this case, hydrogen peroxide decomposing to make water and oxygen here, our products are H2O liquid, can't have a concentration because it's pure water, and O2 gas, which is a gas. This will bubble out. So this reaction, anybody ever dealt with hydrogen peroxide? What do you use hydrogen peroxide for? Cleaning up things, disinfecting things. What does it do when you pour it over? It bubbles, right? So this is that decomposition. That bubbling, what is in those bubbles? What gas is being released? Oxygen. So that's what's going on right here. That oxygen is being released. So in this case here, because I can't have a concentration of a gas, we can measure a gas by its pressure. So what I've done right here, PV equals nRT. What equation is this? PV equals nRT. Gas law, ideal gas law. PV equals nRT, or Pivnert. So if I take the ideal gas law and I substitute it in for concentration molarity, again, molarity is moles per liter, I end up with this idea that the concentration of oxygen is equal to the pressure of oxygen times a factor of 1 over RT. So I can write the rate still as being equal to the change in oxygen over change in time, but as pressure as long as I have this factor of 1 over RT in front. And this is on the bottom, page 611, if you're following along in the textbook. Therefore, a rate can be written in terms of the concentration or the pressure if it is a gas. Concentration if you're aqueous, pressure if it's a gas. It cannot be written in relation to any other measurement. So if you are aqueous, it's written in terms of concentration. If you're a gas, it's written in terms of your pressure. Hello? Why are you not going to the next page? Come on. There. And so this is just showing you how the pressure changes over time. It looks very similar to a concentration curve. All right. So how next does stoichiometry affect the reaction rate? So stoichiometry, that's the coefficients in front of your balanced equation. So here I have, back to the same equation we started with, the bromine plus the HCOOH makes bromide ions, hydrogen ions, and carbon dioxide. And we find that Br minus appears at twice the rate that Br2 disappears because the stoichiometry is 2 Br minuses to 1 Br2 here. So when we're reporting the rate of reaction, we have to report it as far as what are we comparing it to? Are we comparing the rate of reaction to which reactant, or are we comparing it to which product? Because we can write a rate expression in terms of how much a product is appearing. just not a rate law. So let's get into it. This will make sense once we actually look at rate expressions. Let me get to the equation for rate expression here. All right, so a rate expression is rate is equal to 1 over your stoichiometric coefficient times the change in concentration of your reactant over time with a negative in front because your reactant is being consumed. Or you can write it in terms of a product. So if you're in terms of a product, it looks exactly the same way, except we've lost the negative because products are being produced, not consumed. So yes, this equation we're going to be using. So these are called rate expressions. So let me just real quick terminology. Rate expression versus rate law.
So why are some of the letters capital and why are some not?
In this equation, so the lowercase ones, those are your coefficients. The uppercase, that's your actual species. So in the case of here, this would be your lowercase is your coefficient of 2. So if we were writing it in terms of this term right here, the rate would be equal to 1 over 2 times the concentration of bromide ion over time. I think this will make a lot more sense once you actually start doing a couple of examples of them. So 1 over whatever your coefficient is, could be 1 if it's just 1, times how your change in concentration of that over time, negative if it is a reactant. If it is a product, you leave off the negative. Notice these are all equal to one another. So you only write it in terms of one reactant or one product at a time. That is a rate expression. So rate expressions be written. Why does it keep on doing that? Of any reactant or product. As long as that reactant or product can have a concentration or a pressure, which means it must be aqueous or gas. Aqueous or gas. It is negative for reactants. And positive for products. I'm going to leave that one there. Products. And stoichiometry matters. I say that because later when we do rate laws, stoichiometry does not matter. Which is great news for you, right? I know we all love stoichiometry, chapter 3, and beyond. Kept on doing it. So because a rate expression can be written in terms of any reactant and any product as long as they're aqueous or gas, you will have a different rate expression for as many reactants or products as you have in your equation, and they will all be equal to one another. So you'll have the rate in terms of a reactant equal to the rate in terms of you have another reactant, equal to the rate in terms of a product. They're all equal to each other because they're all equal to the rate. All right, let's try this out. Write the rate expressions for each of the following reactions. So reaction A, I have 2 reactants and 2 products, and all of them are aqueous. How many rate expressions will I have? for reaction 1, or A. If I have 2 reactants and 2 products, how many rate expressions will I have? 4. We will have 4 rate expressions. So, for A, what just happened there? I don't know. So the first rate in terms of I, is it going to be positive or negative? Negative, good, because it's a reactant, so I'm going to have negative in front. And then my stoichiometric coefficient is just 1, so we could write 1 over 1, or we could just leave it. Change in concentration of I minus over change in time. And that is your first rate expression. That's all there is to it. Second rate expression in terms of OCl minus. Going to look exactly the same. It's a reactant, so it's also going to be negative. Its coefficient is 1, so it's just going to be 1. Delta. By the way, what do the brackets mean again? When I put things in brackets, what does that mean? Good, concentration of. Now, Cl minus, how is that going to look different? Positive. Good. We're going to leave off the negative because that's a product. But it's still coefficient of 1. And then the very last one's going to look like what? Good. Change in concentration of OI minus over delta T. And there are your rate expressions for that equation. So for B, in terms of ozone, O3, first of all, positive or negative? Good, negative because it's a reactant. Is there going to be a fraction in front? Is it 2 or 1 over 2? Good, back to our equation here. It's 1 over the coefficient, so it's going to be 1 over 2. And then change in concentration of ozone over change in time. What's your second rate expression going to look like? What? It's going to be positive. What fraction is going to be in front? 1 over 3, and then the change in concentration of O2 over time. All right, so now you guys try C on your own. Everybody get those? Not so bad, right? Rate expressions? In the next example we'll put in some numbers here. Yeah. All right. All right, so the importance here is to notice that all of these are equal to one another. So if you write the rate expression in terms of concentration of one thing in the reaction, and you know the rate for another thing, you can solve for one of these rates of either being consumed if it's a reactant or produced if it's a product. So let's look at the next sample problem. which is sample problem 14.2 on page 614. So in this question, it says, consider the reaction 4 nitrogen dioxides plus oxygen makes 2 dinitrogen pentoxide. At a particular time during the reaction, nitrogen dioxide is being consumed at a rate of 0.00130 molar, that's our concentration unit, per second. There's a time. At what rate is molecular oxygen being consumed, and at what rate is dinitrogen pentoxide being produced? So remember back in chapter 5, we were talking about heat, and I said you have to pay attention to the wording to determine if you're going to be positive or negative. If heat was being released, did we make our heat positive or negative? Heat is released. Is that positive or negative? Negative. Good. Whereas if heat was being consumed, that was what? Positive. Okay, here we're talking about reactants versus products. So first of all, we are told that nitrogen dioxide, that is a reactant, is being consumed at a rate of 0.00130. In this case, should that rate be positive or negative? Negative, because it is a reactant. So even though it doesn't have a negative there, we know that's actually a negative rate because it is a reactant. It's being consumed. So let's go ahead and just write our rate expressions here. In terms of everything, just so we have it all there. So the rate in terms of the nitrogen dioxide, negative because it's a reactant. 1/4 because that's the coefficient. Change in concentration of nitrogen dioxide over change in time equals to, in terms of O2, still negative because it's still a reactant, just 1/1. Change in concentration of O2 over change in time. And I could keep on going and doing the N2O5, but let's hold off for a second there, because this is what I'm interested in right here. The fact that these two things are equal. Because I was told that this, the rate at which NO2 is being consumed, is equal to 0.00130. I was told that. So I can plug in what I'm being asked, at what rate is molecular oxygen being consumed. That's this. That's what it's asking you. At what rate is it being consumed? So at this point, we're just plugging in numbers, keeping track of the fact that because this is a rate of consumption, that's actually a negative rate. So I'm going to just plug that in here. So negative 1/4 times negative 0.00130 molar per second is equal to our negative change in concentration of oxygen over time. I ran out of space there, but equal to this. So negative 1/4 times negative 0.00130 should be what? Small number. Starting off with a small number and then multiplying it by a quarter. Should be something times 10 to the negative 4th. Good. 3.25. 3.25 times 10 to the negative 4th molar per second is equal to the negative oxygen over time. So you can bring the negative over, but if it's asking you the rate of that it's being consumed, we're just asking for an amount there. Same as with heat. When it's asking how much heat was released, you would leave off the negative. So that would be your final answer for part A. Would just be the 3.25 times 10 to the negative 4th. Mm-hmm. This right here is equal to that. That's what I did right there.
So on the very end,
Right here, this was me starting to rewrite this. I ran out of space and realized, well, it's here anyways. It's equal. It's the same thing. Yeah. Which is the same thing that they have written right here. Yeah. So then for part B, same thing, but now we're asking for at what rate is the dinitrogen pentoxide being produced. So in that case, dinitrogen pentoxide, we have our rate we just found in terms of the nitrogen dioxide, in terms of the dinitrogen pentoxide. Now we're positive because we're a product, and it's 1/2 because you had a coefficient of 2. So bring the 1/2 the other side, and you take 2 times 3.25 times 10 to the negative 4th. And that's where the 6.5 came from. Start from the beginning there? Okay, let's go. Let me just do a blank slide. New slide.
I just don't know how you multiply by that to
Let's start with our rate expression. So rate in terms of the NO2 would be negative 1/4. Equals, now in part B, we're comparing it to the dinitrogen pentoxide, which is 2 of them, so that's positive 1/2. We were given that this right here is negative 0.0013, 130 molar per second. So negative 1/4, negative 0.00130 molars per second equals 1/2. And this is what we're solving for. What is the rate of change for N2O5 over time? So if we take the 1/2 to the other side, 2 times negative 1/4 times negative 0.00130 molar per second equals the change in why did I do the triangle twice? And this all comes down to that 6.5. That's 10 to the negative 4th molar per second. So that is how to write rate expressions and how to do calculations with rate expressions. Next time, we will talk about rate laws, how to write rate laws and how to determine rate law constants.